Now, we will look at one particular cancer which is breast cancer, and the reason of talking about or discussing this particular cancer is that it is the second largest cause of cancer related death in women. Now, what is why we have to design a sensor or a chip or any kind of actuator to diagnose this particular cancer, tissue related cancer? The reason is that the gold standard, which is the histology, still results in lot of false positive and false negative results. So, our goal is to come up with a sensor that can understand change in the tissue property, and when we talk about change in the tissue property, what are those changes? If you know that when there is a tumor or when this tissue stiffness would be different. So, if stiffness is different, elasticity would be different, right. So, whether this tissue is more elastic or less elastic or less stiff or more stiff, that is one parameter which we will say as mechanical properties of the tissue. Now, depending on the stiffness of the tissue, maybe its composition may also have changed. If the composition of the tissue is changed, that means the tissue can be smooth, tissue can be coarse, right. So, if the tissue is smooth or tissue is coarse, what will change? Resistance of the tissue will change, is not it. So, the change in the resistance of the tissue we call as electrical parameters of the tissue. Now, since there is a change in resistance, if I apply if this is a tissue and if I apply heat on the bottom of the tissue and if I measure the change in the temperature, the given temperature and the measured temperature, this is T1, this is T2. This T2 would be different than T1 depending on the resistance of the tissue. From that I can calculate thermal conductivity of the tissue. So, now we are talking about mechanical properties, electrical properties and thermal properties. So, we are adding 3 modalities, electrical, mechanical and thermal, over and above the existing modality which is biomarkers. So, can you fabricate such sensors that can measure these 3 properties, alright. So, that is the idea. We will talk about one particular sensor which is a piezoresistor, and we will see how can we fabricate piezoresistor using photolithography technique, which I have already discussed with you in detail. But if you have forgotten, then I will just show you quick video about the photoresist positive and negative type and how to coat the photoresist on a silicon wafer. Okay. So, if you see the screen, what you see here is the breast anatomy, and when you look at the breast anatomy, if you see this particular image, then what you will understand that the breast consists of a bigger picture, okay, consists of duct, right, then consists of lobes and consists of fat and finally pectoral muscles, right. This is a composition or anatomy of the breast. Now, depending on the type, like if there is a cancer in duct, then it is called ductal cancer. If the cancer is in lobe, then it is called lobular cancer. If the cancer is in duct as well as lobe, then it is called mixed tumor cancer. If there is a inflammation in the breast, we call inflammatory cancer, and if there is a mucinous, if a mucus is there, then we say mucinous breast cancer. So, you understand these are the types of breast cancer: ductal, lobular, mixed tumor, mucinous and inflammatory. Alright. So, let us go to the statistics. What statistics says? That according to WHO, cancer remains a global health problem. Around 14.1 million new cases were diagnosed in 2012, 8.2 million died in 2016. So, breast cancer continues to be the second largest cause of cancer related death in female in the world, okay, accounting for about 12% of all the cancer. And if you see Indian data, the last data from ICMR in 2016, about 14.5 lakh new cancer cases, and the project that is likely to reach about 17.3 lakh new cases in 2020. It was also this is just cancer, okay, a general cancer, but if you talk about breast cancer, then breast cancer constituted an estimation of 1.5 lakh new cases in 16, marking it number 1 cancer overall from the 14.5 lakh cases. Now, in particularly when you talk about breast cancer, there are different biomarkers. Let's say biomarker A, biomarker B, and biomarker C. All right, there are different names for that: estrogen, prostrogen, and then we say SMA green, and then we also say HER2 plus, HER2 minus. Let's not go into technical things because we are not interested right now for this particular course. What we are interested is that amongst breast cancer, when we see breast cancer, there are three different biomarkers that are generally studied, and if all three biomarkers are absent, then the patient is said that okay, patient is normal, a patient does not have any cancer. But 12% of the breast cancer, say 1.5 lakh, let us say 1 lakh, okay, 1 lakh cases are there of breast cancer, out of which 12,000 cases, out of 1 lakh 12,000 cases, right. Let me write down 1 lakh in this format. So, out of 1 lakh cases of breast cancer, 12,000 cases are triple negative breast cancer. What is triple negative? All three biomarkers are absent, and if all three biomarkers are absent, that means the person is normal, but in reality person has cancer, alright, and that is a difficult part. That is why if we can design a sensor that can identify the change in the tissue property and we can correlate that with the existing gold standard, then we will be able to diagnose cancer probably with much more accuracy, alright. So, that is the idea. So, if you see the table here, then you will understand that for women, if it is breast cancer, which is 29% of the women, then for the men it is 26% cases when it comes to prostate cancer. So, as dangerous breast cancer is there for women, for men it is prostate cancer, alright. And then there are other cancers like lung, colon, urinary bladder, right, thyroid, leukemia, melanoma, which is skin cancer, kidney cancer, renal cancer, it is a uterine corpus, right, cervical cancer, and many more. Okay. So, what exactly from the statistics what you understood? We understood that worldwide it is estimated that 1.68 million women were diagnosed with cancer in 2015, which means 1 in 8 women will be diagnosed with breast cancer during their lifetime. In United States, if we say more than 2,32,714 breast cancer cases were diagnosed, out of which 43,909 women died. Thus, for every 5 or 6 women newly diagnosed, 1 is dying. Very sad to see these figures. Now, let us think and look at the figures from our country, which is India, and here if you see that breast cancer in India, around 1,44,937 cases of cancer, breast cancer in 2015, out of which 70,218 died. You can see this figure. This is 2,32,714, 43,909 died. It is 1,44,937, 72,108 died. That means for every 2 women newly diagnosed, 1 is dying when we talk about India. And the reason, probable reason, is that the screening is not done as per the routine, as routinely as it should be done. That means that women should go to a health center to screen for any possible abnormalities in the breast. Alright. So, if we are aware that there can be screening like mammography, right, and that mammography can probably help us to diagnose or at least screen the patient, and patient can be diagnosed with the histology at early stages, then the cancer can be cured. And that is why if you see the figures from the United States, it says that for every 5 or 6 women newly diagnosed, 1 is dying, because if let us say 5 is diagnosed and 1 is dying, 4 of them are diagnosed at extremely early stage, right. In our country, because of the not enough awareness about this particular cancer, and in general about lot of cancer, generally people do not go for routine checkup, and that leads to the higher number of death when it is diagnosed, because already the cancer it is at the higher state or higher stage. Alright. So, let us see again screen that the current adult women of all ages are encouraged to perform breast self test at least once a month, and for mammography, which is a screening tool, every year if the woman is between 40 and 54, she should go and perform the checkup. If it is every 2 years for 55 and above. So, if you talk about MRI, you can see that there is a lump here, right. If you go about mammography, again you can see a lump here, right. When this kind of suspected region is identified, a patient has to go for breast biopsy. So, biopsy needle is used to take out the tissue, and that tissue is sliced with the help of microtome, and this slice are used for immunohistochemistry and spatial staining. There is this P63 brown and SMA red. I said SMA green earlier, that just ignore that, SMA red and P63 brown, while there is a ER is estrogen, PR is prostrogen, and HNE. So, these are the staining methods to understand whether there is cancer or not. And what we will do is that since the oncopathologist may not require the entire tissue, we will ask to get this particular tissue for our SEM images and another tissue for our experimental data or for our experiments. Alright. So, we will see about this later, but if you see here, what you see is there is a breast tissue here which is about 5 millimeter in length, and you can also see from SEM images, which is right over here, that the normal tissue, which is this one and this one, and cancerous, which is this particular one and this particular one, these 2 images are cancer and this is normal, right. Then the normal region looks much more smooth compared to the cancer region, or in other words, cancer region looks much more coarser compared to the normal region. Alright, we will talk about this microgrid sometime later. So, let us go to the next slide, and next slide is a very important slide, because here what we are understanding is how to design a piezoresistive microcantilever. You see, if I have a diving board, right, in a swimming pool, this becomes a cantilever. Now, we are talking about cantilever which has a thickness of about just 2 microns and with a width of about few hundred microns, and there is a piezoresistor embedded or integrated onto it. So, that is using a diffusion technique, and we use here boron for diffusing the piezoresistive material onto the silicon wafer, right. And we will also discuss this thing, how can you create this particular piezoresistive material. Then the width, like I said, is about few of 100 micron. The thickness is also, length is also few 100 microns. Let us say length is 200 microns, width is about 100 microns. Just don't worry about it, the diagram is not up to the scale, and the thickness is about 2 microns, all right, and on this we are depositing an SU8 tip. SU8 tip is, so if you see this particular figure, this is the tissue and this is the cantilever, this one is cantilever, and the SU8 tip is on the bottom of the cantilever. So, if you look at my hand, if this is the tissue, right, if this is the tissue and this is the cantilever, because see this is the like cantilever, right, then this is SU8 tip. When you fabricate it becomes like this, but you have to place like this and then you press it on this particular tissue. So, this is the moment that we will do. Now, depending on the thickness of the tissue, depending on the stiffness of the tissue, not thickness, stiffness of the tissue, my cantilever will bend, right, because there is a SU8 tip that will indent. When it indents, depending on the tissue, my cantilever will bend. This bending will cause strain in the piezoresistor, and that will change the resistance of the piezoresistor. That means that depending on the stiffness of the tissue, the cantilever will bend, and correspondingly the resistance of the piezoresistor, which is integrated onto this particular cantilever, will change. What is piezoresistor? When you apply force, there is a change in resistance, isn't it? So, if you now see the figure, you will understand that when I am talking about this particular image, there is a cancerous tissue, breast tissue, normal or cancer I do not know, let us say breast tissue, and the SU8 tip is the bottom of this cantilever, right, bottom of this cantilever, and if you see this particular chip, then you here what you see is that the piezoresistor cantilever, the contact all the way it goes to here, okay. This is a sensor contact. I do not know whether you can see very clearly or not, but this is how it goes all the way here to here, and this is how it is, it goes here and all the way here, and for here this is how it is, okay, and the cantilever is here right at the tip of it, right. This is a silicon chip. So, the contacts of the from the piezoresistor are all the way here, this is contact pads, right. So, you take the contact from these two regions when there is a change in the piezoresistor, the resistance value of the piezoresistor, and that change will be there depending on the elasticity of the tissue. So, when you indent the tissue, there will be change in the resistance of the tissue. Here you can see is a microcantilever about 100, the length is close to 120 microns. There is a piezoresistor embedded onto the or into the silicon wafer. It is a P type material which is boron. We have used diffusion technique to integrate the sensor. If you want, you can also read our paper, which is mechanical phenotyping of breast cancer using MEMS, a method to demarcate benign and cancerous breast tissues. This is in a journal Lab on a Chip. It was published in 2014. Okay. So, further to understand, that is what I have drawn earlier. You see this contact pad is all the way here, all right. It is continuous line. The detailed dimensions are given in this particular image. You can see that 40 microns, yes, is the width, about 130 microns is the length, this particular cantilever. The piezoresistor, when you talk about, the width is 10 microns, spacing between two piezoresistive line is 10 microns. The spacing between two contact pads is about 2000 microns. The overall chip size is about 4000 microns, which is 4 millimeter. The piezoresistor length from the contact pad to the end of the piezoresistor would be 60, but from the silicon wafer edge to here is 30. You see here is 30 and then another 30 is 60. Anything else? Yes. So, that is what it is here, and then you have a SU8 tip, which is a probe tip. The thickness is about radius is about 5. So, diameter is about 10, and I am sorry, the thickness is close to 50 microns. 50 micron is the thickness of the tip. So, you can see here now, you see this tip, right, this is a SU8 tip, and these two pairs that you see are these pairs, let us say P1, P2, this is P1, P2. This thing you are not even looking in SEM, you cannot see the complete chip at least in this image, alright. And here you can see this lines, right, this is all etched using deep reactive ion etching technique. So, here what we have used is DRIE to etch the wafer and fabricate the piezoresistive cantilever. Now, if you see this particular image, again you can see SU8 tip, cantilever is released, this is silicon nitride, green one is silicon nitride. We will etch it later on, I will show you in the process flow which is right over here, and yeah, there is nothing else to see on this particular image. So, let us come to the process flow, alright. So, if you see this process flow, we start with SOI wafer. SOI means silicon on insulator, alright. So, where is silicon on insulator here? You see the grey color is silicon, this one is silicon, this one is silicon, green color is SiO2. So, this silicon which is layer 1, right, this is layer 2 or the substrate, layer 1 is on silicon dioxide. Silicon dioxide is what? Silicon dioxide is insulator. So, silicon on insulator which is SOI, right. So, our first wafer that we will select for fabricating piezoresistive microcantilever will be silicon on insulator or SOI wafer, alright. Second step is to grow silicon dioxide, right. So, you be with me, okay. Let me write down here, this is step 1, step 2, step 3, step 4, step 5, 6, 7, alright. Let us see 7 steps first. First one is your SOI, second one is you are growing silicon dioxide, correct. Third one is you are creating a window by using photolithography, and in photolithography you will protect all the area except this particular area when the window is created. Dip the wafer in BHF, silicon dioxide will be etched. Next step is you diffuse boron resistor which is yellow color in picture here, alright. So, the resistor value will be different than the boron contact value. So, let us see the colors here. If I am sure that you can see the same colors. So, here is purple, purple is for silicon nitride, green color is for silicon dioxide, grey color is silicon, golden color is gold, orange color is for boron contact, blue color is for SU8 material, and yellow color is for boron resistor, alright. So, now if you understand these colors, then what you will understand is first is our SOI, second is we have grown silicon dioxide on SOI wafer, third step is where we have created a window by performing photolithography, fourth one is we have diffused boron resistor again by photolithography, because here if you spin coat boron everywhere, then the boron can only, let us say this red color thing is boron everywhere, okay, everywhere. Then when you diffuse it, boron cannot pass through silicon dioxide layer. We will select silicon dioxide layer such that the boron cannot diffuse through silicon dioxide layer, but boron can diffuse through silicon, and that is why you can see here a boron resistor, alright. This is a cross section of course. The next step would be we grow again silicon dioxide, and then the next step. So, this step number 5 we grow silicon dioxide. Step number 6 is we create a window so as to diffuse boron contact, and in the next step which is step number 7 we have diffused the boron contact. The reason of diffusing boron contact along with boron resistor is that boron contact will give a ohmic contact when you deposit chrome gold. If you directly take contact from boron resistors, you are not guaranteed to have the ohmic contact. After this particular step, the next step is you deposit chrome gold everywhere. So, you assume that this chrome gold is everywhere, alright, and you perform photolithography such that you will only have the contact pairs, alright. So, this one would be our mask number 8, right. I will just write down in this letter. So, I am not using Roman anymore, but if you want to see, this one is 1, 2, 3, 4, 5, 6, 7 and this one is 8. So, after that, after this boron diffusion, boron resistor diffusion, boron contact diffusion, gold diffusion for creating contact pads, the next step would be to deposit silicon nitride and pattern it as shown in step number 9. Alright, here. So, you deposit silicon nitride everywhere and then create window. Next step would be, which is step number 10, would be that you etch silicon dioxide and silicon through this window, right, using your RI and DRI. And the 11th step would be you spin coat everywhere SU8 and then do lithography such that you can only have SU8 tip, which is protected here, is step number 11. Step number 12, what you do is, in step number 12 you create a window from the back side of the wafer, and in step number 13 you etch this silicon completely still you reach the silicon dioxide. So, silicon dioxide is a mask, will act as a mask when you etch it in silicon etchant, and thus what will happen, that here the etching will stop. When etching stops, then you can put this wafer in the RI to remove silicon dioxide, or you can use BHF to remove silicon dioxide. You need to be very careful, and that is how you have your piezoresistive microcantilever. Let us again quickly repeat so that you understand. Step number 1 would be silicon on insulator. The silicon cantilever thickness depends on the thickness of this particular silicon wafer. Alright. Second step would be you grow silicon dioxide on the SOI wafer. Third step is you create a window. Fourth step is to create diffuse boron resistor, and fifth step would be grow silicon dioxide. Sixth step would be to create window. Seventh step would be to diffuse boron contact. Eighth step would be to spin do deposit chrome gold and pattern it using lithography to form the piezoresistive contact pads. Ninth step would be to create windows. 10th step, ninth step would be to deposit or grow silicon nitride and then create windows. 10th step would be to etch silicon dioxide and silicon nitride, silicon dioxide and silicon from the windows. And step number 11 would be you spin coat SU8 and create a tip. Step number 12 would be you do front to back lithography. You see, in this particular case there is a front to back lithography, right. It should not, see, if you do not properly perform lithography, what will happen, that you cannot release this cantilever. Alright, only cantilever region should be protected, other region should not be protected. So, now or in a way that only cantilever region, this everything should be etched, right, except cantilever. So, that for that you have to perform the front to back lithography, which is your step number 12, and finally you etch it in DRI, which is step number 13, to get your piezoresistive or to realize your piezoresistive microcantilever. And then the application, as you have seen, we can use it for indenting the tissues. When you indent the tissues, depending on the elasticity of the tissue, the resistance would change. So, let me play 2 videos. One is on the photoresist coating or lithography, and the second video is on the silicon dioxide. The silicon dioxide in particular we are using PECVD. The reason of using PECVD in silicon dioxide is that we can use the system at a lower temperature. But if you do not use PECVD, if you go for the thermal oxidation, then you have to grow silicon dioxide at extremely high temperature. You do not want that, you want to grow silicon dioxide at a lower temperature, and PECVD, which is plasma enhanced chemical vapor deposition technique, will help you to grow silicon dioxide and silicon nitride at lower temperature from 100 degree centigrade to 400 degree centigrade. So, let us play the video, and then second video would be about the spin coating of the photoresist. Again, 2 photoresist you will see, positive photoresist photoresist and negative photoresist. So, let me play the videos.
Hello, today in this video we'd like to talk about photolithography. Now photolithography is a process where you take photoresists or the solvent that is sensitive to light. Now this light spectrum is usually in the UV, so whenever you do photolithography, you're going to be working in this yellow room. As you can see, the room around me is yellow, and the hood is a little bit orange, but they both serve the same function, and that is to filter out UV light. So photoresist comes in two general categories. We have positive photoresist and negative photoresist. Positive photoresist works by being exposed to UV light and becoming weaker, so you can use a mask to reveal areas you want to get rid of. While negative photoresist is the opposite. Whenever it gets exposed to UV light, it gets stronger. So areas that are exposed are kept, and the areas that are not exposed are removed. Now in our facility, we have two separate rooms for each kind of photoresist. In this room, the hot embossing room, we only do negative photoresist. We have another room down the hall that is dedicated to positive photoresist. Now, the same tool is used in each case. We have a Leroy spinner right here. Now the Leroy spinner is designed to take your photoresist, put it on a substrate, and evenly distribute it so you have a nice uniform layer. So before we start using this tool, you have to log in to remove the interlock. Without the interlock removed, the tool will not light up on the screen and it will not let you use it. So to log into the tool, our laptop is over here. And this location has two tools, so make sure you're logging into Leroy 3 spinner. As you can see, I'm already logged in. However, if you come here and you see something like this, now, right now it's set up for the AMB UV, which is another tool that we use in photolithography. If you see the screen, you can simply switch to Leroy 3 by clicking this side here. The drop-down menu comes out, and just click Leroy 3. And I'll switch over. See how I'm back to Leroy 3? And then you can log in as normal. So once you've logged in, we are now ready to approach the tool. When you first approach the tool, there's a certain condition the tool should be in before you start using it. First, you want to make sure these two valves right here are perpendicular to the line. That means they're closed. You see how it's perpendicular? To open them, you turn them so they're both parallel. You should hear a small hiss coming from the back. That means they're open, and it's good. So the reason why we have to keep both these lines open when we use the tool is because it provides functionality to our spinner. This line here is a nitrogen line. It provides nitrogen gas to the chamber of the spinner. This is important because it keeps the environment inert inside the spinner and prevents any kind of gas from leaking into the motor and possibly causing a reaction. The line here, the vacuum line, is important because it sucks in and holds your sample on the chuck. Without this vacuum line, your sample will not stick to the chuck as it spins. It will fly out. So it's important to have them both functional and working. This is also why we keep them closed. By keeping them closed when the tool is not in use, we're preventing any kind of buildup from getting into these lines, which will make the lines either harder to open and close or not functional at all. Now the vacuum line is provided by the building. If you ever hear a loud noise opening this line, as you see, there's no loud noise. It'd be pretty obvious. That means there's a problem with our vacuum line. You should report it to staff as soon as possible because this is provided by the building and we have to notify them to make sure that there's no problem upstairs. This hood on the top of the Leroy spinner should be closed. We want to maintain an inert environment, so you want to make sure all the gas is just going to sit there and it's not going to be exposed to anything else. We also want to make sure this is clean. As you can see right now, it looks pretty clean. You don't see any kind of epoxy-like material or photoresist anywhere. The surface should not be sticky. See how it's really smooth? And inside, in particular, it should be pretty clean. If it wasn't clean, you'd see a drip down of photoresist coming down here and dripping to the bottom, but you don't see it here. The photoresist is pretty viscous, so it drips down slowly. You might not see it immediately, so it's always good to inspect the inside as well. You also want to make sure that your logged in has enabled the screen. The screen will be blank if you're not logged in, so that just says the interlock is working and the tool appears functional. If the tool is not clean or if any of these conditions are not met when you first arrive, please inform staff. We want to make sure that these are followed rigorously. Now, the reason why this is so important is for two things. The Leroy spinner itself uses an electric motor which can be the source of ignition for fires. So if these are on, the vacuum's on. And if the vacuum's on and you don't clean this adequately, it's going to suck in photoresist. Most photoresist is flammable. So if the wrong condition happens, maybe a spark, maybe something like that happens, the whole thing can ignite. and that's not good. Another thing is we don't want photoresist to go inside and clog the valves. On this chuck here is a small hole. Now, when you don't clean the photoresist around the tool, it can actually crawl and get sucked into here, which goes in this hole. As you can see, it's a little dirty in there. You see how the photoresist is in there? Someone didn't follow this direction, so you can see it's dirty. That will eventually get clogged inside. And if it gets clogged, the vacuum line won't work. And if it doesn't work, then you can't spin the photoresist. So it is all very important to follow so that we keep our tool up and running and prevent it from getting damaged. Alright, so now that we've done all our preliminary checks of the tool and the surroundings, we're ready to start using it. So whenever you do any kind of spinning on photoresist, you want to pre-process your sample or your wafer. And this can involve RCA cleaning, piranha cleaning, or any kind of other process like HMDS. Once your device or your wafer, in this case I have a simple ordinary silicon wafer, is ready, you can start using the tool. So this chuck here has a vacuum in the middle. This vacuum is going to hold the wafer down. So when it spins, the wafer won't fly out. It's very important that your sample is bigger than this chuck. Now if you have a smaller sample than this chuck, that means some air is going to be sucked in around the edges. If that's the case, you must mount your device on a bigger chuck size or substrate like this. So if I have a small little glass piece, I put it on top of a wafer like this, and then put this on top of here. When you mount this on top, you want to have it centered. So when it spins, it's not lopsided. That's going to give you a more uniform coat. So when you open the valves earlier, pressing vacuum here will initiate the lock mechanism here. You see that V equals equal to 25? That's the vacuum pressure in millimeters of mercury. You want at least 16 for a good hold. We have 25, which is more than enough. So now that it's holding, personally I like to spin it a little bit. As you see, it's kind of wobbly. It's not centered. So I like to make adjustments. It's better now. It's never going to be perfect, but you don't want to have it obviously lopsided. So once you've done that, your sample is ready. You want to blow with this nitrogen gun to get rid of any loose particles that may have landed while doing this loading process. Typically, we store our photoresist in flammable cabinets because photoresist, as you know, is flammable. So for SU8, we keep it underneath here in the SU8 resist storage. Inside, you'll find a couple of secondary containers. Please store your photoresist in these containers. These are important because if the bottle ever leaks or breaks, it's not going to drip all over the floor. It's going to stay isolated in here. Now, bottles should be clearly labeled. We have to know what it is. In this case, SU8. We need a PI. It should not be expired either. This has not expired, so this is good. Usually we throw away unlabeled or outdated bottles, so make sure you're on top of that. Now, ordinarily, you could pour from the bottle directly to your sample, but if you have a very low viscosity SU8, I recommend using a drop it. So with that out of the way, let's talk about how we're going to dispense it. So I'm not going to do it in the video, but if you have a viscous solution, you could just pour it in carefully and do it slowly. If you have a dropper, you just drop it in. You want to apply it in the middle, and you only need a little bit. You don't need to use it much. I'm not going to say how much you need because that really depends on your photoresist. There's always a manufacturer recommendation, and I would recommend using that volume. It tells you per square centimeter how much volume you need. So once you have that settled, you can close it. Here's where you program it. So as you can see, there's a couple of buttons here. If you hit F1, you'll see PGM on top. That means it's in programming mode. Then you can use the cursor to adjust RPM. Right now, it is 500 RPM, and the acceleration is 224 RPM per second. Now, this varies according to your process, so I'm not going to say what's right or wrong. You have to check your process and see what your steps are required to be programmed. So, if you need multiple steps, you can always add or delete steps. So, right now we have 2 steps available here. Most SU8 requires 2 steps, but if you want to do a more complicated routine, you can definitely add more steps. To program the other steps, you hit the step button. Under here, you'll see 2 out of 2. Earlier it was 1 out of 1. I'll press it again so you can see it. Now it's 1 out of 2. So this is the step you're programming. The second step, as you can see, is 3,215 RPM. The acceleration is a little higher, and the time is different. The time was over here. Right now this is 35 seconds. Over here it's minutes. Always double check what you're going to spin. You want to make sure you hit step and read everything so that it's the right formula. Now, the reason why we use these formulas is because higher RPMs give you thinner layers of SU8 when you spin it. And it also depends on viscosity. So this is a very important step in your fabrication. When you're done here, you can hit F1 again, and the program will go away and it'll say off. Now, assuming your vacuum is above 16 and you have no errors, you should be good to go. Now, to run it, you hit run and stop. You run it. You see the timer starts going, and you see that the wafer visibly spinning. It's going to spin for the exact recipe you put it for. Now, some complications that can occur, you will see on the screen right here. See how it's met? The top is what it wants to spin, and the bottom is what it's spinning now. If there's a problem with the rotor, you will see that it's not going to spin the right speed. It might be lower, or it might be above. So always keep note of what's happening here. Also, if you see a Cba error, that means the nitrogen feed is not working. It could be because you didn't open it. It could be because something's wrong with the line. So just keep awareness on this little screen. It'll give you errors if there are any. Now, assuming there's no errors, you get this nice little end, and nothing will pop up, and your sample will be ready. What you want to do is open this and take your sample out. There's a lot of ways of doing this. Personally, I like to grab it underneath because you have photoresist all over the top at this point. Right now, there's none. Then you can pull it out and carefully move it to an oven. Ordinarily, I would wear a particle mask because that's going to prevent you from breathing on your sample. But since we're not actually spinning SU8 in this video, I'm not wearing one. Also, I want to be more audibly clear. So SU8 generally has two baking steps. We have a 65 degree and a 95 degree step. The manufacturer actually recommends that you use a hot plate, and you can use a hot plate on any metal bench, which we'll show a bit later. But we also provide these ovens for your use. These ovens are usually preset, but you still want to check the temperature on this thermometer up here. Right now it's a little bit above 65, which is fine. It's the right setting. Now, something very important about these ovens is you want to make sure the doors are properly latched. You see how I'm pulling on it? It's not coming out? It's because it's latched. If you do not latch it, see how it opens up? It should not be openable. To close it, you want to pull it, make sure this is over a clip, and then it clips down. Now, if you leave it open, the oven's going to burn itself out. Basically, what's going to happen is it's going to try to reach a temperature that it can't reach. So it's going to just keep going and going and going, and it's going to burn a fuse, and then it's not going to work. So then we have to replace it, and it's going to have downtime. So we want to avoid any downtime. The other oven is over here. This oven is set at 95 degrees. And again, I would check with the temperature to make sure it's the right setting. As you can see, we have several trays. You want to make sure these are aligned. Some of them are a little bent, so you don't want your sample to creep. You want to make sure it's on a flat surface. When you close this, you want to make sure it latches too. Many times people will just leave it like this and see how it's open. You don't want to do that. It has to click. And then when you pull the door, it shouldn't open. That's how you know it's properly closed. So once your sample is baking, this is a good opportunity to start cleaning the spinner. Now, you only want to clean when you're done spinning everything. So I recommend if you're doing 3 or 4 wafers to spin them all first, so that all you have to do is clean once. So the cleanest spinner, you want to use acetone. It's usually located on this side of the hood. And it's denoted by this red bottle that clears as acetone. If this bottle is running low, we usually have spare bottles over here. So this yellow cabinet is meant to store flammable chemicals. Acetone is flammable, so we want to make sure we always store it in here. inside you'll see a nice inventory. We have acetone right here. We usually have isopropanol, which is isopropyl alcohol, and methanol. You want to make sure this is properly closed. So see how I kind of just pushed it, but it's not really closed. You see it's still open. You want to open the latch, push it, and close the latch. You want to make sure to do all the pouring in the hood. I didn't bring one because we have plenty of acetone here. But if you were empty, for instance, you would bring the bottle over here, pour it while in here, and make sure you don't breathe any of the fumes, and also put it back in storage. I know some users like to do this, and I want to address this. Some people like to put a chuck like this on it, turn on the vacuum, and spin it while spraying in this little hole. Now that's not good for two reasons. First, you're getting acetone everywhere, and some of the pieces, like the motor I mentioned earlier, might get sucked into that area with the electric motor, and it might be a source of ignition, so that's dangerous. Second, you're splattering SU8 and acetone kind of everywhere. It will leak out here and out here, and you're just going to make the whole area dirtier. The better way to do it is not to use this chuck, but instead to wet a clean wipe like this, give it a nice amount, and scrub it out. So you want to reach in and just wipe the walls. It's clean now, but when you wipe it, you'll see a lot of gunk building up. So try to get as much as you can, and when you think you have enough, you can dispose of it over here. This yellow can is meant for SU8 and solvent wastes, which includes acetone, methanol, and isopropanol. You put it right in, and keep going. It takes me a few wipes. You can't do it in one, unless it's a very small mess. Now, when it's very smooth to the touch and not sticky, that's when you know you're done. That's when you know it's clean. Everything should be smooth. Here, 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 and inside. Now, another area you should clean is underneath this piece. So how do you remove this piece? Well, if you see underneath here, this little thing right here, you want to grab onto it and spin the top. It will unscrew itself, and this comes out. Then you can get this out here, and you can spray with acetone and wipe it here safely. Because here it won't get sucked into the motor, and it won't get sucked into the tubing. You don't want to spray it directly on here because it'll get sucked in. So here it's safe. You just drench it, you clean it, you take off the chuck, clean in there too. And then when it's clean and smooth, you can also clean the walls here that are hard to reach and underneath. So you're just going to wipe and wipe it. When it's done, you put it on the same way. You hold this little stick here, and you see the screw, just screw it back in. When it's in good condition, you should be able to spin it freely. So see how I give it a little bit of push and it spins? Right now it's not so great, it's a little dirty. You want to see it do 2 revolutions at least. Right now it's doing maybe 1. So it's almost due for a good cleaning. But if we all take these steps to clean the inside and clean the surroundings, we can prevent this from happening and keep the tool up longer. Alright, so once the spinner has been cleaned thoroughly, you want to make sure you close these 2 valves over here. Remember the rule, if it's perpendicular, it's closed. If it's parallel, it's open. Think of it like a flow, and see how they're kind of crossing the flow? It helps you remember. You also want to close this, and put this back on the right side. You want to make sure these cabinets are closed, if you took out Photoresist, and then lastly, you want to log out. Now, the next step that we usually have in SU8 processing is the exposure. For most situations, a single mask is enough, and for that we use the AMV-UV, which is right here. The login is right next to the roll spinner, and as I said earlier, you can use the drop-down menu to switch to this tool. This tool is covered more in depth in another video. If you have more than one layer and you need alignment, we have another tool called the MA56. It's in another room, in the lithography room, and that's also covered in another video. So, assuming you've done all of the processing, including the baking and the UV exposure, and you're ready to develop, then we come over here. This is our development bench. The lights are right here. Notice I already set up here, but usually you don't want to leave things laying around. So to develop, you want to use SU8 Developer, which is usually stored down here, where you see SU8 Developer. SU8 developer is pretty universal, so this will develop almost every SU8 that I can think of in this facility. But I would check just to be sure. You want to put it in here, and you want to open it carefully. Typically, you only need enough SU8 developer to cover the sample. So I'm going to bring over a sample very quickly. I'll just pop it in. Next, I'm going to pour very carefully, just a little bit. You don't need a lot. That's all you need. Now, SU8 develops faster if you agitate it or if you use an ultrasound machine. The INF provides an ultrasound machine that you can borrow. Typically, this can take anywhere from 1 minute to 20 minutes. It really depends on how thick your SU8 layer is. For thicker layers, more development time is needed. But the most importantly, I want to stress, you don't need that much developer. Any more than this is wasteful. As you can see, it just only covers. The last step in SU8 development is to check whether or not it's actually developed. So when you think the time has gone by, you can take out your sample with your tongs. Make sure it doesn't drip out. And use isopropanol, which is the yellow one here, labeled isopropanol. And you spray your wafer. You do it very slowly and gently. You don't have to splatter it. Just kind of take your time. Just slowly get both sides. Just make sure it's thorough and just take your time. Notice I'm using a separate container to catch this. You don't want to mix the developer, and I'll explain why in a second. So then you can dry it off here. I like to use a clean wipe and just etching in here. Slowly. This gun speeds up really fast, so you want to slowly ramp it up, or else you might blow your sample out of your tongs. So if this had SU8 on it, you might see some white streaks. That means it's not done yet. And if it wasn't done, what you would do is just stick it back into the developer and give it more time. Now once you're done, I'm going to show you where to dispose of everything. First of all, you got to make sure this bottle is closed and put it back where you found it, which is down here in the SU8 developer. Next, we have to do two different kind of wastes. We have SU8 developer and we have isopropanol. Now isopropanol, methanol, acetone are all considered mild solvents, and we have a different waste container for that. Ordinarily, we can just take it out. Here's our solvent waste, which refers to mild solvents. And you can open this. We have a couple of funnels we can just use and throw it in. Make sure this is closed tightly, because all of these will evaporate out and fill the room with solvents, and that's not good for your health. So you want to make sure it's contained in that container. Next, we usually rinse these. So what you can do is put this in the sink and run some DI water in it. You see it's a little soapy. That's normal. You keep rinsing it until the soapiness kind of goes away. I'm going to speed it up a little. As all things done in the clean room, you want to take your time. So you don't want to rush this. Just let it run. Go put away samples, things like that. So you see some bubbles, but it doesn't look soapy anymore, which means it's pretty much rinsed off. I'm going to close the line, not all the way, just enough like this to lower the pressure. Reach in and then just give it one more rinse. Just kind of carefully. A lot of users like to leave their samples here to dry, and that's fine, but you want to remember to pick it up. Because if you don't pick this up for a few days, we're going to put it somewhere and it might get lost. So you want to make sure you keep track of your beakers. Now the SU8 developer is not thrown in there, but in a different place. Under here you see waste developer. You see a bottle designated SU8 waste developer. So you want to put it in here, bring out a funnel, and carefully pour this in there. For this, I like to rinse the funnel a little bit with DI water before putting it back down there, just as a courtesy. Just some low pressure water is enough. Secure the cap and then take it out. Put it right underneath. If there's no more bottles to use for waste, we have a separate room where we contain waste bottles. You can ask staff for help if you don't know where this is. So right now I'm just going to rinse this last container, but that pretty much concludes photolithography for our facility, and thank you for watching.
The Unaxis PECVD, or Plasma-Enhanced Chemical Vapor Deposition System, is used to cause gases to react in a high-frequency induced plasma in order to deposit dielectric materials onto substrates. The Unaxis PECVD is a single-chamber system capable of depositing silicon dioxide, silicon nitride, silicon oxynitride, silicon carbide, polysilicon, and p-doped polysilicon. All users should contact the trainer for the system prior to depositing any type of polysilicon layer. The Unaxis PECVD can process a wide range of sample sizes. The number of samples depends on the size of the samples. A typical run can process up to 4 4-inch wafers. Typical deposition rates range from 60 to 600 angstroms per minute. Now go over the various parts of the Unaxis PECVD. The process chamber is where all the processing takes place on the system. The two main parts of the process chamber are the showerhead and the platen. The showerhead is used to evenly distribute the gases in use during processing. The platen heats the samples to improve the deposition quality and increase the deposition rate. The system's computer monitor and keyboard allow you to control the software for the system. The software enables you to vent and pump down the process chamber, select or create the appropriate recipe for your process run, adjust the parameters of your recipe, and initiate the process run. The status window within the software displays the chamber pressure, the heat exchanger temperature, and the watt low or platen temperature. All of the available gases are listed on the right side of the screen. The info, warning, and alarm message windows are intended to make users aware of any actions being taken by the system or any problems that may be encountered during a process run. All users should be mindful of the buttons located at the bottom of the screen and their functions. The run button should always be highlighted during a process run. If this is not the case, you should notify an MRC staff member immediately. The standby button may be used if you are editing the parameters of a recipe, but it is not essential to a process run. The ready button should always be highlighted unless the machine is in standby mode. A process will not run unless the system is in ready mode. The board button should never be used under any circumstances. The end step button can be used to terminate a step before it is finished. The hold, run, and alarm buttons will be discussed later in the video. The system is also equipped with an emergency shutoff button, which should only be used in the event of an emergency. Now, let's introduce our lab users. Before you can begin using the Unaxis PECVD, you must first log into the system at the access controller. Once you are logged in, you should begin venting the process chamber. To do this, you must first open the Utilities drop-down menu located at the top left-hand corner of the screen, and then select Vent from the list of available options. You should be able to hear the chamber venting during the venting process. Once the chamber is vented, the system will initiate a 60-second overvent step. The gates will close automatically once the overvent step is completed. Even though the chamber may open prior to the completion of the overvent step, it is recommended that you keep the chamber closed until the entire step has been completed. Once the chamber is vented, you should begin cleaning the chamber. To do so, you must first locate the vacuum, which should be located next to the system. There should be a flattened metal attachment connected to the nozzle, which was specifically designed for vacuuming the system. That partly across the platen as well as under the platen. Do not vacuum the rubber seal because this could cause it to become damaged. Instead, wipe the area around the seal with a text wipe. Under no circumstances should you ever touch the shower head. If you happen to notice material flaking onto the platen from the shower head, you should notify an MRC staff member so it can be cleaned manually. Do not leave text wipes or any other item or material that could possibly melt inside the chamber. When heated, materials such as plastic are prone to melt and leave behind residue, which could in turn lead to contamination issues inside the chamber. Therefore, it is imperative that any tools you may wish to use, such as tweezers, not be made of anything other than metal. You should never use any kind of chemical inside the chamber as well. It is possible for them to ignite and/or produce dangerous fumes if they are heated. Once you have finished cleaning, you may load your sample into the center of the chamber. Once your sample has been properly positioned, you may close the chamber lid and prepare to pump the chamber down. Before running a recipe, you must first pump down the chamber. In order to do this, you must open the Utilities drop-down menu and then select Pump Chamber. Chamber cover down until the rough pumping is complete. To select and run an existing recipe, you must open the Process drop-down menu and then select Load Recipe. The name of your recipe should appear in the process window. If necessary, select the Ready button and then select Run. The process will begin once you have selected the Run button. Do not try to open the chamber door when the process is running. The chamber is pressurized and will not open. Attempting to open the chamber could result in the handle being damaged. When the process run is completed, open the Utilities drop-down menu and then select Vent. When the system is vented, you may open the chamber and remove your sample. When you have finished using the system, you should perform the same cleaning procedure used earlier in the video in order to keep the chamber clean for future users. Do not restart the system computer. It can only be restarted by a staff member and will be unavailable for use when it is down. We will now create a new recipe by editing an existing recipe. In general, a recipe should have 5 basic steps: the initial step, the gas stabilization process step, the deposition process step, the nitrogen purge step, and the end step. For the purposes of this training video, we will be editing the standard oxide recipe. From the process menu, you should choose to edit an existing recipe. All of the standard recipes start with STD in the process menu. To edit a step, double-click on it. All recipes start with an initial step. This step will cause the chamber to evacuate and bring the plate into the desired operating temperature. Set the pressure to 10 millitorr and the time to 30 seconds. This will cause the system to evacuate as much air as possible before starting the process. You should not attempt to use pressure set below 10 millitorr. The chamber will still evacuate as much air as possible regardless of the set point. At this point, you should set the temperature to your desired process temperature. Note that the temperature is measured in degrees Celsius. You should not set your temperature below 150 degrees Celsius or above 300 degrees Celsius without first consulting the trainer. The heat exchanger temperature should also not be adjusted. You may describe your recipe in the description box. The first few words will be displayed by the file name when you are loading your recipe. Once you have done this, click OK. Double-click on the first process step. This step stabilizes the gas flow rate and sets the process pressure. Because the RF power is off, no processing will actually take place during this step. The process step dialog box has 4 major areas: time, pressure, gas flow, and power. The first process step's terminate by time should be set to fixed time. The time is not critical, but 30 seconds should be sufficient. Leave the power set to 0 in the first process step. You should also set the gas flow rate for each gas here. Flow rates are given in SCCM. Set the pressure you want for the process in units of millitorr. The system is optimized to run between 900 and 1100 millitorr. The second process step is when deposition of the material takes place. If you set its terminate by time to variable time, you will not be prompted to enter the process time each time you run your recipe. This is more convenient than editing your recipe each time. However, you can set the process time to fixed time and set the time here if you prefer. The pressure and gas flow rates should be the same for both process steps. You should set the power for the second process step. Make sure not to exceed 400 watts. Okay, once you have done this. The fourth step is a 5-minute nitrogen purge step at 100 millitorr. This step is necessary to remove any trace amounts of gas, which are very toxic even in small quantities. You should not under any circumstances skip the step or end it early by clicking the end step button. This is for your own safety and for the safety of other cleanroom users. The final end step is when evacuation of the chamber takes place. Set the pressure to 10 millitorr like you did in the initial step so that all the nitrogen is removed. The automatic vent feature gives you the option of venting automatically after the process is complete, or leaving the chamber pumped down until it is manually vented. You may set this to your preference, but the standard recipes should always remain manually vented. After you are done editing a recipe, you must save the file. When you modify a process, you only change the copy on the disk. If the process is already loaded, you will need to reload it for your changes to be reflected. You should name your recipe by the first letter of your first name, followed by the first 2 letters of your last name, followed by an underscore, and then abbreviate the name of the material that is being deposited. Now, save the recipe. After watching this training video, you should have a pretty good understanding of how to clean the chamber, load a sample, run a recipe, program a recipe, and unload a sample. If you have any questions, please direct them to the trainer of this equipment. Please do not ask Charlie.
Okay. So, what you see, you have seen in both the videos, the first video was on lithography, which is more on the spin coating of the photoresist, and the second video was focusing on the PECVD technique, right. So, now let us see each step in detail, and what I would prefer is that you see the screen so that you have some idea about what we are talking about. If you see the screen, what you see is first step would be your silicon on insulator material, next step would be to grow silicon dioxide. So, we do not bother. After that, if you want to quickly see how lithography can be done, I will just show it to you here one step so that you understand other steps by yourself. This is silicon dioxide here, alright, and silicon dioxide on the back side. So, this is our step number 2. Okay. What I am showing is how to reach to step number 3, how to create this window. So, creating window, you spin coat photoresist, alright. So, I am spin coating my positive photoresist. Next step is you soft bake it at 90 degrees centigrade for 1 minute on hot plate. Next step would be you will load the mask such that this will be dark field mask. You know two types of mask, bright field mask and a dark field mask. This will be dark field mask because we have used positive photoresist, and the properties of positive photoresist is that the area which is not exposed under UV light will be stronger, the area which is exposed will be weaker. So, now this is your positive photoresist, this is a positive photoresist, this is your mask and your mask is dark field mask. After this you will expose your wafer using UV lithography or UV light, right, and next step would be photoresist developer. When you develop the wafer in photoresist developer, what will happen, that the area which was not exposed would be protected and the area which was exposed in UV will get developed. Next step would be you perform hard bake. Hard bake is done at 120 degree centigrade for 1 minute on hot plate. If you perform hard bake, the next step would be, so what is this, silicon dioxide, then you have silicon, then you have silicon dioxide, then you have silicon, here again you have silicon dioxide. So, if I dip this wafer in BHF, what will happen, I will dip this wafer in BHF, then what will happen, we can etch silicon dioxide from this particular region. So, what I will have is right. If I dip this wafer, if I have dipped earlier wafer in BHF, BHF will etch silicon dioxide and other silicon dioxide will be protected using the or with the positive photoresist. The next step would be, I will dip this wafer in acetone. If I dip this wafer in acetone, what will happen? My photoresist will get stripped. If my photoresist gets stripped, then what will I have? I will have my step number 3. So, from step 2 to step 3, this is the lithography process. You got it? Easy, right? Now, step 4, same way. What is next step? Step 4 is we have to diffuse the boron here, step 4, right. So, boron is diffused. Next step is you again grow silicon dioxide. So, silicon dioxide everywhere, right. When you diffuse boron, what will happen, you know, when you diffuse boron, there will be borosilicate glass. So, some borosilicate glass would be there. So, you have to dip this wafer in again a BHF. So, when you dip this wafer in BHF, what will happen? This silicon dioxide and everything will get etched. So, you have to regrow silicon dioxide like this, and that is why you can see this particular step, this is 4, this is 5. So, this 5th step you can see silicon dioxide is again grown, is not it, after diffusing, and then you again create a window, and this time what you will create, where you will create window, you will create a window such that this window would be overlapping a part of the boron diffusion, and this is for what, this is silicon dioxide. So, you are creating window for diffusing boron with a higher concentration or so that the conductivity is high, and that is used for the boron contact, and this is what you have done in step number 7, right. In step 6 you have opened the windows, step 7 is you have now created the contact, right, and this is the contact of the piezo resistor. When you create the contact of the piezo resistor, if I want to see the top view is like this, silicon is there, everywhere silicon is there, and earlier what I did is I just created or I just diffused the piezo resistor material like this, and this is my boron resistor. Then everywhere there was silicon dioxide. I just open window here and window here, and again diffuse the boron contact. So, I have boron contact all the way here, sorry, which will overlap my my piezoresistor. So, this is what is overlapping, this contact that you see on this particular image, right, this one is this particular part, this is boron contact on the boron resistor. Okay. So, this is top view. So, you have to just keep on imagining that where are we, which step, or the what will be the front view, what will be the side view. These are all the cross section view that you can look at when you are talking about the process flow. This is called a process flow for fabricating the piezoresistive microcantilever. So, first, second, third step is over, fourth step over, fifth step over, sixth and seventh step is also done. After this, like I said, whenever you have so after you diffuse boron contact, the next step would be you deposit chrome gold everywhere, right, like this, and then pattern it such that you can only have contact. So, that was the piezoresistor, right, like this, and this was the contact, right. Next step would be you create further big contact like this, right. This will be chrome gold, this will be chrome gold, all right. This is what we are talking about in step number 8. After that, you grow silicon nitride everywhere, right, and then open window such that you are now starting fabricating your cantilever, all right. So, next step number 9 would be you deposit silicon nitride and open windows. Step number 10 would be that you dip this wafer in silicon, first is silicon dioxide etchant, which is BHF. So, this silicon dioxide will get etched, followed by DRI, which will etch your silicon, and it will not etch silicon dioxide because silicon DRI will not affect silicon dioxide, as silicon dioxide will act as a mask. After that, 11th step would be, so after this, okay, the 11th step would be you spin coat SU8 and then you again do photolithography such that only this region is protected. This is your 11th step. Step number 12 is you create the front to back alignment and etch silicon dioxide from the back side, followed by silicon nitride from the back side, followed by silicon dioxide. So, first is you can use RI to remove silicon nitride, then you can use BHF to remove silicon dioxide, or you can only use the RI technique to remove silicon dioxide and nitride both. After this, you can see that silicon is visible, and this silicon you can etch with DRI to form your piezoresistor, microcantilever with integrated piezoresistor into it. Okay. So, once you have that, this is a inverted microscope, and we have loaded the tissue microarray onto a glass slide, and this is the indenter or a piezoresistive microcantilever which is indenting this particular microarray, and these are the corresponding tissue microarray biomarkers which will help us. The green boxes that you can see in each one of this particular tissue are the region of interest. BE stands for benign, B stands for benign, C stands for cancer, E stands for epithelial region. So, let us say B is benign, E is epithelial, C is cancer, S is stromal. So, now if I say BE, that means benign epithelial, CE cancer epithelial, BS benign stromal, CS cancer stromal, all right. So, you can see here different nomenclature, and these are tissue samples from different patients, patient 1 to patient 8, and when you indent you can get the different readings. We will see this particular what kind of readings you get in the next class. Till now, what you have learned? You have learned how to work in a clean room, then you have learned what are the clean room protocols, then you have learned what can be, how can we fabricate piezoresistive microcantilever for understanding the tissue property. We took example of a breast cancer. Then we have seen the process flow of how to fabricate cantilever. While working on the process flow, I have just shown you 2 more videos which were on the PECVD, because we will be coating silicon dioxide at lower temperature, and another video was for the photoresist. Followed by, we have seen how can you take the indentation, can you use the piezoresistor for indenting the tissues. The next class we will see how can you, what kind of data you get when you indent this, as well as we will continue with the electrical sensors for understanding the resistance of the tissue. Alright. So, till then you take care. I will see you in the next class. If you have any question, feel free to ask us in NPTEL forum.